So this is Sami Kallinen with Sailing with Scicloj, a Bayesian adventure. But first, a word from our sponsors. Presented by our lanyard sponsor, Otto. This talk is presented to you by Otto, the largest German online store and marketplace for thousands of brands and partners. As a technology company, they employ a variety of tech specialists, from AI to MarTech, from online marketing to IT, and much, much more. So without further ado, let's hear from Sami.
Thank you. Super nice to be here today. I've done all kinds of things, but around 3 or 4 years ago, I started shifting towards full-time Clojure programming. I'm with 8-bit Sheep. It's in Helsinki. We specialize in tech and data stuff. But I'm also with, let's go here because my controls don't work so well. I'm also with KP System. In Växjö, in Sweden, we are developing a full-stack Clojure application that is used by Swedish municipalities. There's a great Clojure team there, so it's a good opportunity for remote work. So please check out for any open positions that we have. But okay, with that out of the way, let's go into why we are here. I guess we are all here because of this fantastic thing called Clojure. But I'm also here because of Scicloj. It's an amazing community that develops data science tools and libraries for Clojure. Furthermore, I'm here because of this demo today. It has been prepared in collaboration with Daniel Slutsky. We want to show you a real-world data problem to demonstrate what you can do with the Clojure data science tools currently. For the demo, we have collected some data while we've been out sailing. And this is the boat we were sailing with. I have to say, I had a whole section about how I ended up sailing, which was a kind of slipped on a banana peel, and about this boat. But you'll be relieved to hear that I had to cut it out because it didn't fit the 30 minutes. But you can come and ask me. I will talk endlessly about it later. Jonnekin. And don't ask me what it means. I had very, very long conversations trying to translate it. But I guess the last one we settled on was yonder, if that gives you an idea. But OK. Today, our goal is to predict vessel speed based on the wind conditions. So why do we want to do that? Because of these things. They're called polars. Don't worry about how to read them right now. I hope by the end of this talk you might have an idea. What should we do with polar charts? Why do we need them? So we need them if we do racing, which I don't do. We need them if we need to do weather routing. It's an important piece of data for these applications. And also something I call quantified sailing. But yeah, let's look at, if I find my mouse. So what we're doing here today is that based on the wind strength and the wind angle here, we want to predict the velocity. There are, of course, many more variables involved, but let's keep it simple for today and have only these two predictors. And we are sailing and collecting data. Actually, I wasn't collecting data here. This was 4 years ago when I started. But let's start even simpler in the beginning. We'll ignore the wind strength, or we just pick one wind strength. Imagine the universe only has one wind strength, 6 knots. If that doesn't mean anything to you, maybe this does, or this, or some of us want our wind strength in meters per second. It's not a lot, but it's just a random one that we've chosen. So we need some data to work with. Like I said, we've been collecting some experimental data, but let's also leave that to the side for now and begin with some synthetic data. The idea is that we prefer synthetic data when we start modeling because we know how it behaves. We know what kind of noise there is. So it's much easier to debug and develop our models when we have something that we understand very well, not the noisy, messy empirical data. So we start with data that looks like this. All the wind speeds are 6. And we have different angles, and we have different velocities. This data was generated by an external library based on some dimensional data inputs that we gave about our specific boat. So you could think of this data telling how our boat, or a boat like ours, should ideally perform, if kind of a potential how it could perform. And this is how the data looks. Also notice how nicely and easy it is to make a simple plot like this with the Scicloj tools. If we go here, in the y-axis we have the boat speed, the velocity. This is our outcome variable. That's what we want to predict. And here we have the angles. And you see that at 0 angle we have 0 velocity, and that makes sense because no sailing boat can sail straight into the wind. Also here at the end we have 180 degrees. That's basically when the wind blows from behind, so you're sailing downwind. But you might wonder, what is this slope then? It goes pretty quickly up when the degrees increase here, and then it goes down. So this has to do with that when we're sailing downwind, the sail works like a parachute. It drags the boat along. But when we're sailing with a side wind or a beam, when the wind is from the beam, like you say in sailing lingo, or from when we're going upwind, the sail works like an airplane wing. So it generates lift, and it's much more efficient. You can actually, even some boats, foiling catamarans, can go faster than the wind because of this reason. Okay, so we're doing some smooth sailing again. This was actually this summer, and we were indeed collecting data, and this was downwind. It's the Baltic archipelago in the southern parts of Finland. But okay, let's start modeling. Yeah, so let's start learning the ropes and get busy modeling. You see what I did there? Regression is a statistical tool used to uncover the relationship between variables. And we'll start with a simple one like this. And this is the one that we want to fit. And again, we have the velocity here, and we have we want to predict the velocity given the angle. And we have 2 parameters, or weights, if you like, that we want to find the optimal values that will fit the data as good as possible. Here's the code and the plot. I'll look at this a little bit more. We're doing this for demo now. But to be honest, to do this regression line you saw, you could just add 1 parameter to the Hanami cloth plotting, and you would get that. But we're going to use this same way of doing almost the whole of the presentation. So I'll go through it quickly here. So we have the data. We give it to something called create design matrix. We define something here that we could call a formula. This is basically what we want to predict, and these are the predictors. Here's only one, it's a very simple one. And this basically forms the data into something that this training function will understand. So it's very easy to express what kind of polynomial, for instance, you want to use for predicting. Then you train, and that will output a model. You give it to the predict function here. I know it's illegal to use this kind of threading here, but don't tell anybody. We give some angles, and we get some predictions, and we fix a little bit the data, and we do the plotting like you saw there. So here we have it. No surprises, perhaps, but it's safe to say that this model is pretty terrible. So let's make another terrible model and add the wind variable to the mix. And I remind you, we are using wind strength and the wind angles as predictors, and we wanna have the velocity as an outcome. And now we add one more term here. We have the wind term, and it has its own parameter. And when we're doing this kind of modeling, these parameters always will have one single value. It's a certain combination will generate the model that we're having, but it's a single value, and this will be important later. We need to change our plotting function because now we need to examine the model as a three-dimensional surface instead of a line. So here we have it. So if you look at down here, we have the wind again, as we had in the two-dimensional plot, and the angles from 0 to 180 here, and the velocity up here. And this plotly has a nice 3D plot that you can sort of study and get an intuition how it looks like. And like we said, unsurprisingly, this is still rather bad. It doesn't look anything like our data. So let's make one of those formulas I talked about earlier. We want to predict the wind, and we do something a bit more complex here. My hunch is that something called a cubic polynomial would maybe fit much better. The way we see the data points look like, a cubic polynomial could be a better fit. And now it's the same pattern, but we have 7 parameters. Again, these are single values that we search to fit the data as good as possible. But before we do the modeling, let's add some more data to the mix. So now, in the last example, we had 4 winds. Now we have wind speeds from 4 till 30. And keep in mind that this is still the synthetic data, the theoretical data. A sort of a theoretical estimation of how a boat like ours can perform optimally. But there are some problems here. You can see them maybe. We have a strange little thing here. And this spike is likely an issue with the external library that we use, a numerical problem. The library is a rather large blob of object-oriented code, not Clojure, by the way. So it's quite difficult to debug. But for us, this is okay. It's even maybe good, because our model needs to be able to handle these kind of anomalies without overfitting, without sort of taking these aspects into the model. So let's look what the cubic model will look like. Yeah, it's not too bad, actually. It's pretty good. Ideally, yeah, we have kind of most of it on both sides, which is sort of what we want. And the general shape is pretty good. And if we look at, I have a mouse, not to have this more easier. If you look at this spike here, the outliers, this model deals with it very well. But we do have some problems as well. In our sort of world, velocities that are negative don't make any sense. Let's make that a little bit more visible. We'll create a custom gradient. Was the spots? We add red as the first color, and then we continue with the gray scales. And now we can see much more clearly all these values that are red are bad. We don't want them. And this is actually shortcoming, which is not very surprising. This is how polynomials tend to work. They might become erratic at the edges. But let's go with this model regardless. It does perform well up here. And actually, this part is not so interesting when we're sailing. These sort of low angles are not you never sail that high into the wind in any way. So we can sort of live with this for now, I think. And we did try many other algorithms, and most of them tended to overfit and take the other errors here. So this was a good compromise. So now we have a basic model that we could use, but we still have some questions. So remember, we have these measurements that we made. How do we combine the knowledge we have in this ideal world of the synthetic data and the measurements that we do? How do we reason about the different assumptions that we're going to make when we go further? And we really want to know the uncertainty of our results and also be able to reason about them in a way that makes sense to us. So basically, we're looking for an intuitive mental model to continue this work. Oh yeah. So yeah, we're getting, I couldn't see it here, so we're getting into deeper waters, some higher higher seas, complex territories. So this is, by the way, on our sail between Gran Canaria and Tenerife a while back. Yeah, let's take our lifeboat. Maybe that's a bit too dramatic, but Bayesian statistics in any way, let's start looking at that. So this is not a lecture about Bayesian statistics. I would probably not be qualified to give one, but I tried to give you a really simple intuition of what it is. So what if we want to find out if this coin is fair? This coin I actually took from, that's our kitchen table on the morning before I flew here yesterday, but not very important, but anyway. If this coin is fair, in the Bayesian approach, we would write a probabilistic program that not only simulates and tracks all the coin flips, but also generates all these coins, and they all have different fairness in them. And then we just look and measure what this simulation says. That's basically one way of explaining. So in the Bayesian analysis, both our data and the things that are unknown to us are treated just as variables in the probabilistic program. And the program defines all the relationships between all the variables in the polynomial, in the estimated velocities, which we want to get as outputs, the empirical data, and the synthetic data. You could think of it like logic programming, but we also add some uncertainty into the mix. So sort of logic programming plus uncertainty. Then you just need to run the algorithm or do the simulations. That's your modeling step. And then you start looking at the data you get out of it. So you could think of it like a data log query, but then with some randomness inside. Not sure if this helps you understand what Bayesian statistic is, but at least I tried. So we have the same polynomial here again. Like we said before, these in the previous approach, these are all single values that we find that generates the model that you saw. But in Bayesian analysis, we view all of these parameters not as a single fitted value, but as variables in this probabilistic program that they have uncertainty. So it basically means they are distributions. And this allows us to reason about the likelihood of the different parameters in our model, but also eventually the different estimated values, like the estimated velocity. And that's really what we're interested in, to understand not just the model, but also how likely the different values are. Yeah, so to do probabilistic programming, we need to use a tool for it, and we have here been using something called STAN. It's a probabilistic programming language, and it can be used in Clojure with a Scicloj library called command stan CLJ. it's kind of C-like. You define, Stan itself is C-like. You define input data, what the parameters have, what kind of types they have. And here we have our polynomial, do some modeling, and these are some prior distributions for our parameters. I won't go deeper into that now, but it's easy to use. What we do here is we just run this code you just saw, and Stan creates a binary that will receive the data that you defined in the program we just saw. That's all you have to do. And then when you do the sampling or the simulations or the modeling, whatever you want to call it, you just need to make the data into a format that Stan wants. It's basically a map with keys as the input variables and the corresponding data set. And then you run this sampling function. You can do some configuration. Then it starts to churn, do the simulations, and eventually we get all the distributions out as samples, just as data. So it's a very data-driven approach here. So before we run this model, let's add the actual empirical data. So here, these ones are the synthetic data, and these are the ochre ones are the data points we've been collecting throughout the summer. And if you eyeball this, it kind of looks okay. It sort of has the same shape, but you have much more variance here, which is normal because you don't go absolutely the optimal full speed all the time. You have reasons why you don't want to do that. So it will be more, you will have lower numbers here as well. And the reason why you don't have any points here is because luckily we weren't sailing in storms or gales. It was quite good weather when we were out. Okay, now we combine this, and this approach that we're using allows us to actually do that in a meaningful way. But before we look at the results, I want to show you, do a little digression and show you some diagnostic plots. This is because when we do sampling or simulations, which is the modeling process, there are no guarantees that it will work. We might have to change our program. There can be many reasons. So we need to diagnose it, that it actually did work. And now, in the interest of time, you just have to trust me. This looks very good. This is how it's supposed to look. If you want, it's actually not very difficult, simple, but it would take too much time to explain how it works. But this is how we want it to look. And if you want to know more, just ask me later. So now, this is the result. And yeah, now we have two surfaces. And the point is that actually each sort of point in the grid we are plotting here has a whole distribution of values. And what we've done here is that these surfaces mean that according to our model, the velocity values should fall between these two surfaces 80% of the time. This looks pretty good. It has the same problems, of course, because we're still using the polynomial underneath. But yeah, it's maybe a bit wider than I would have hoped for, but it's explained by the how much data we have and this variation I talked about before. But it's quite beautiful. It's nice. But maybe another more concrete way of looking at the same data and these samples is that we could take one data point from the empirical data. We were sailing 175.5, or this is the angle, which is more or less wind from behind, downwind. Our wind strength at the time was 10.6 knots, and our velocity was 4.1 knots. And this distribution here is the distribution of the synthetic data. So the sort of optimal capacity of boat like ours. And although we're not far, if you look at the sort of peak, it's here around a little bit more than 5, maybe 5.2, and we're 4.1. 1 knot is not actually a huge amount of difference. It is if you're sailing like over an ocean or something like that. But we can see that it's very unlikely, according to this model, that we would have this speed is super unlikely. It's really here at the edge. So we should do much better, basically, based on this. But now when we add the experimental data, the data that I've been collecting, it's actually, we are pretty close to the sort of expected value, the top. Most of the values in the simulation are suggesting that we would have speeds like this. And this reflects our style of sailing. Our real boat, it can differ from this imaginary boat we have in the synthetic data. So actually, what I find interesting here is to start, you could start debugging our boat based on these two differences. Why is it like that? So are we too heavy? Is the boat too heavy? Should we get new sails? Should I learn how to sail better? That's for sure the case. But anyway, this is exciting. And actually, I could have this real time while I'm sailing, so you could get it as a feedback. So that's what I was referring to as quantified sailing. You can sort of follow how you're doing. And another representation of this is the polars. Ta-da! This is where we started. And I promised that we could, you could maybe read it better now. And this is just like the first 2D plot we looked at, where the wind angles were at the x-axis and the speed, the velocity was at the y-axis. But now the wind angles are in a polar coordinate system. And it might seem a little bit complicated to draw it like that, but think of it. For a sailor, this makes a lot of sense, because your boat is heading that direction. Where you're standing in the boat, this is exactly the direction where the wind comes from. So that's why we use, or people use, this representation for the same data. Yeah, so I'm pretty happy. It looks good. There are some issues. The polynomial does that. If you look at down here, it doesn't make sense that it goes actually in this angle. It should sort of even out and go as a straight line here. So that's something that we take because of the polynomial we are using. And there are other options, and we will continue to actually work on this model and hopefully also post some blogs. Okay, so I think the exercise is ready, but we set out to sort of take some problem and see if we are mature enough, if the tools, Scicloj tools are here to do it. And I would say, from my experience, they definitely are here. And this was not the case just a few years ago. We can do pretty complex analysis with Scicloj. And that little dolphin is very happy we're doing Bayesian analysis there. We filmed this outside of the Gibraltar Strait a while ago. Just a few short shout-outs. We were using these dependencies to do this exercise. There's a lot to say about them, but not so much time. I only say that Noj is one Scicloj tool that is released today. There's a release today, and it collects all of these tools into one curated package, both the documentation and the libraries, so it's easier to figure out what tools to use. And yeah, there's also open, if you want to learn, like the first lecture, doing open source stuff, we have a nice mentoring program where people can join to start doing open source work. It's very popular and it's great. Please take advantage of that. And some heroes who made this presentation possible, especially Daniel, who actually literally we worked on this together. Been doing a lot of pair programming the past few weeks. Okay, that's me. Thank you very much.